So when we talk about the mass of many isotopes of the same element, we're talking about something called the average atomic mass. And remember, average atomic mass isn't something, it's not a standard average. So you don't just add up all the masses and then divide by the total. What you have to take into account is the percent abundance of each of the different isotopes. And so we call that a weighted average. So just as a quick refresher, we're going to do a totally made up, completely imaginary example problem here. So let's say, just for the sake of this example problem, that I have an atom that has two isotopes. And one isotope has a mass of 89, the other isotope has a mass of 91. My isotope that has a mass of 89 is 75% abundant. So of all of the atoms of this particular element, 75% of those are the 89 isotope. The other 25% are the 91 isotope. Now, I can't just add up 89 and 91 and then divide by 2 to get 90. That would just be a standard average. Instead, we have to do a weighted average. So we have to take these percents into account. So the first thing you have to do is convert percents to decimals. So 75% is going to turn into 0.75. 25% will turn into 0.25. And so now I'm going to take each of these decimals and multiply them by the mass and then add the two together. So I have 0.75 times 89, and then I have 0.25 times 91. And then when I go ahead and do that math, my weighted average comes out to be 89.5, which tells me that since my weighted average is closer to 89, I have more isotopes with a mass of 89 than isotopes with a mass of 91. Now, the big question is, how do scientists even know what the different isotopes are, let alone what their abundances are? Well, that's where something called mass spectrometry comes into play. So mass spectrometry, or mass spec, is one way that scientists can analyze different compounds or different elements to figure out their different ions. So this is a diagram of what this apparatus or instrument would look like. And so down here at this side is kind of the start. So the example in this drawing the example is magnesium. So over here you'd put a sample of magnesium atoms. So that's a mixture of the isotopes of magnesium. And then the magnesium is going to be ionized. So it's going to be heated up and it's going to be broken apart so that it turns into its ions. And then those magnesium ions are going to go down this tunnel and they're going to be accelerated, so they're going to move really fast. Now, if the different isotopes have different masses because they have different numbers of neutrons, how far they can travel is going to change depending on their mass. And so that's what we're looking at here. We're looking at how much they're deflected. So the lightest one is going to move the closest to the negative side. The heaviest one is going to move the farthest from the negative side because the particular magnesium atoms have positive charges. So the positives are going to be attracted to the negatives. Now the lightest is going to be the most attracted, so it's going to move the closest to that side. The magnesium 25 is going to go right down the middle, and the magnesium 26 is going to go over to the side. Now from that, it's going to go all the way down here, and then there's a vacuum pump to get rid of the ions. Then at this end, there's a detector that's attached, and that detector is looking at how many ions, how many particles are hitting at that particular spot where they're expecting the different masses to be. And so what we get is this type of mass spec graph. And so on our y-axis, we have the percent abundance, and on our x-axis, we have the mass to charge ratio. So that tells us what the different isotopes are. So in this particular case, the isotope magnesium 24 has the highest abundance. 25 is just a little bit lower than 26. And so you see these straight lines on these graphs, and that tells the relative abundance of each of the different isotopes. And so that's one of the main ways that scientists can analyze to figure out the abundance of the different isotopes in a sample of a particular element.